three concepts: linearity and uniqueness and ownership. And these are sort of three words that you always hear thrown around at this kind of conference. And it's really well known that these things are related in some way, but it's much less well known what exactly the relationship is between these things. What are the relative benefits, strengths, and weaknesses of these things? Can we capture all those different benefits in maybe a single programming language? So that's what we're going to find out. We're going to use our research programming language Granule, and we're going to see if we can get these three things to peacefully coexist in our language. And this talk is going to be a high-level overview of that. This is just a little sort of recap of my research career. The important parts are that I've just been doing a PhD at the University of Kent with my supervisor Dominic Orchard. We work on the Granule language, which is where all this work in this talk has come from. Recently, I've just started a postdoc at the University of Glasgow, working on something a bit different, mailbox types, but this talk is mostly about work that I did during my PhD. So first of all, we should probably think about what exactly the overlap is between these three ideas. And the sort of idea is something that I'm sure everyone at this workshop knows very well. While some data is unrestricted and we can use it however we like, that's not always true. Some data is resourceful and we have to treat it like a resource. That means there are restrictions on how we're allowed to use it. We can't always take a piece of data and copy it as many times as we like. We can't always take a piece of data and throw it away. We might need to do something with it first. And we definitely can't always mutate a piece of data, especially not if someone else might be using it at the same time. And all three of these kind of type systems, these kind of ideas, are all about dealing with how to prevent these things from happening in certain cases and in their own ways. And the first one we're going to talk about is linear types. Now, the analogy that I always like to use when I'm explaining linear types is that a linear type is like a delicious piece of cake. Why is that? Well, you can only eat a cake once, but you live in a sad world where this is true. And if someone makes you a cake, you probably are going to have to eat it, otherwise they're going to be a little bit disappointed. So these are the rules of cakes and also the rules of linear types. And here's how that looks in a real-life programming language. This is Haskell with the recent linear types extension, which has just been sort of added in. So if you look at the types ignition here and what's going on in the function, on the left-hand side we have a value called cake. On the right-hand side we use that value twice. So we use the e function to produce a value of type cake and half function to produce a value of type cake. But because this value is linear, which is sort of indicated by this lollipop-shaped function arrow in the type signature, this is not allowed by Haskell. We can't have our cake in easy 2 because we used it twice on the right-hand side. And just to give you an idea of how our language looks, this is how that looks in Granule. This is very similar to the Haskell example, except with a couple of differences. The first difference you might notice is that we use a single colon for the type signature rather than 2. Some might argue this is the correct decision. I'm not going to get into that too much, but
no question.
Yeah, a question about that?
No question.
Oh, okay.
No question.
Fair enough. The other major difference is that instead of the lollipop arrow, we have this regular-looking function arrow. This is because Granule has what's called a linear base. Values are linear by default, and so just writing the function normally here already implies this value is linear and has to be used once. You might wonder, well, if values are linear by default, that's kind of restrictive. What if I want to use some value in an unrestricted way? We can still do that because we have this bang modality from linear logic. So here we have this value of type bang, cake, and that just means we have as much cake as we want. We can generate more cake as we like. So this is a fun toy example, but in practice, how does this look with a more sort of practical example? So here we have an example that uses file handles. You can think of this I/O thing here as just as if we're in the I/O mode in Haskell. It's a little bit more complicated, but we don't need to worry about that for the purposes of this talk. So on the first line here, we open a handle to a file, maybe a recipe for a cake, maybe not. On the second line, we read a character from that handle, so we get back the handle and the character C. And then on this last line, we return that value. Yes?
Can I ask a question about your first example?
Mm-hmm.
Do you need the let binding? Could I just use lots instead of cake?
Yes, you could. It's just in there for the purposes of making it clear what's going on.
Thanks.
So this file handle example is doing what I just said. But the nice part about linear types here is if I was to make a silly mistake while I was writing this function, which some of you may have noticed, I forgot to close my file handle, then the linear type system would catch this error because I never used this handle h prime on this second line of the function. And so linear types are allowing us to catch a mistake that we wouldn't have been able to notice otherwise, just with the type of the function. So this is great, but one of the sort of selling points of Granule, over and above linear type systems like the one in the Haskell linear types extension, is we can go beyond just pure linearity and nonlinearity. So starting from linear logic, we have linear values and we have values wrapped in the bang modality, which are nonlinear, that we can use however we like. This is great, but it's kind of a restrictive sort of binary view. There are more cases that we might want to consider than just this. So we might think about extensions such as bounded linear logic, which came about not so long after linear logic originated, in which we have a whole family of modalities where we have the bang, but the bang is indexed by this thing R. And what R does is it gives an upper bound on how many times that thing's going to be used. So we can say, for example, I have something that can be used at most 3 times or at most 5 times, rather than just once or any number. And we can extend this further, and this is where the type system of Granule, these graded model types, come in. Now, instead of just having an upper bound on the usage, we have indexes R on this modality, which we use a bang instead, we use a box instead of a bang here, sorry. And these grades or indexes R can come from any pre-ordered semi-ring. This is just a sort of general algebraic structure that encompasses what we had above, but now depending on which semi-ring we choose, we can say different things about the values and how they might be used. So I'm going to give a few examples of this. Just a quick point about notation is that in Granule programs, rather than using this prefix modality where the grade comes after the box, we write the modality postfix after the type, and we put the grade inside the box. So this is how you're going to see these things appearing on the next slide. So the first example is a semi-ring with 3 elements, 0, 1, and many, sometimes called non, 1, and tons, thanks to Conor McBride. So these 3 elements just mean what they say on the tin. 0 means you can't use that thing at all. 1 means you have to use it once. Many means you can use it any number of times. So it could be 0, could be 1, could be any other number. So here's a quick example. Just like we had with the bang modality on the previous slide, here we use this many grade, but this just says we have lots of cake. We eat 1 cake, we still have lots of cake. Another semi-ring is the semi-ring of exact usage, the semi-ring of natural numbers. So here, we grade the value by a natural number, and that natural number tells us exactly how many times that value has to be used. So if you think back to when you were a small child, you probably remember being told at least once that if you have 2 cakes and you eat one of those cakes, then you're going to have 1 cake remaining. That's what this sort of function is encoding here. Now if you think back to when you were a slightly older child, you might also remember being told that if I have some number n plus 1 of cakes and I eat one of those cakes, then I'll have n cakes remaining. So we can use polymorphism here to be a little bit more general about what's happening. One more example just to make sure that the idea is clear here. So this one is slightly more complicated, but just shows you some of the more interesting things you can do with these grades. This says that I maybe have a cake, and I also have a cake with this interval grade. So this is the interval between 0 and 1. So then on this first line, if I don't have the first cake, then I eat that graded cake. On the second line, if I do have the first cake, then I don't bother eating the graded cake. Now both of these lines are allowed because what the interval grade means is I'm allowed to use that variable of type cake, any number of times that fits within the interval. So because on the first line I use it once, the second line I use it 0 times, this isn't allowed according to this grid. So just a few examples of how that works. But now let's think about how uniqueness and ownership fits into this kind of framework, because all I've talked about so far is linearity and how we can extend that, which is where Granule sort of started. But this is kind of where my research comes in, and the next few slides are basically based on my ESOP paper from a couple of years ago, where we thought about how to connect these different ideas for the first time. So just like with linear types and cake, I have an analogy that I like to use for uniqueness and unique types. I like to describe them as being like a fresh cup of coffee. Now, why is that again? If we have some coffee that's just been poured, then we know that that coffee is fresh. Unlike with the linear cake, we can share that around if we want to. We can share our coffee with our friends. What we can't do is share coffee with someone else but tell them that it's still fresh. That again would be quite a weird thing to do. And so here's an example of that in the functional programming language Clean, which looks quite similar to Haskell, but this is where uniqueness types were sort of originally popularized and sort of came into the mainstream. So here we have this value of type coffee. We have this star here. That means that this is a unique type, so it has to be used uniquely. So again, what we do is we use that thing twice on the right-hand side. So we drink our coffee to make us awake, which I kind of wish I could do right now, thanks to the jet lag. I'm sure some of you are in the same position. But we also keep our coffee to drink again later. But what's happening here that we're not allowed to do is that on the right-hand side, we're still saying this coffee has a unique type, even though we created another reference to this variable over here on the left sort of side of the tuple. And we're not allowed to do that. If we wanted to write this function, this would have to be a non-unique value now. So, okay, that's great, but maybe from those two examples, it's not entirely clear what the difference between uniqueness and linearity are, because those examples did look quite similar in the end. And if you look in the literature for some answers here, you might end up even more confused, because some places will tell you that one of these kinds of things is a variant of the other. That's kind of true in some ways. Some places will tell you these things are dual to one another, which makes them sound very different, and that's also true in some ways. But still maybe not quite clear how are they different and how are they the same. So the way that we found useful to think about it, and if you happen to have cited my ESOP paper, this one sentence is unfortunately what you probably cited the paper for, because that seems to be what everyone is doing, is that unique types are a guarantee that a value has never been duplicated in the past. So they tell you what's happened before. Linear types, on the other hand, they don't tell you anything about what's happened to something in the past. It could have come from a bang modality, so there could be any number of other references floating out and about. But what they do tell you is that I can't take that value and duplicate it or throw it away in the future. So linear types are a restriction on the future, while unique types are a guarantee about the past. And this gives us the key insight that we need to think about how we can use both of these things in the same type system. So if we start with linear values as our basis, and we have what's sometimes called Cartesian or unrestricted values under the bang modality, as we already have in Granule, you saw that earlier on, we can introduce a third kind of value, this kind of unique values. We add an additional modality that represents these values. We use the star to make it similar to clean, just for familiarity. And then how do we get in between these three different kinds of value? Well, we know we can take an unrestricted thing and pull the thing out of the bang modality and end up with a linear thing. But it's fine to go from unrestricted to restricted. We also know that we can take something that's unique and share it as long as we don't carry on pretending that it's a unique value, so we can go from unique to unrestricted. But what we can't do, unless we're in some very special situations, is go from linear to unrestricted or unrestricted to unique. We have to move in this direction. And so this is how our overall system works. And in Granule, the two key rules for working with unique values are, first of all, we have this share rule. This just embeds the idea that we had on the previous slide, where I can take something that's unique and I can share it, which means I can then use it as I like. I'm just not saying that that thing is the unique reference anymore. We also have this clone rule, which is slightly more interesting. So what this says is that if I have something that's unrestricted, and I know how to take something unique and use that to do some kind of computation, then what I can do is I can take the unrestricted thing, make a deep copy of it so that I have a new kind of whatever value that is. And since I've made a deep copy, that copy is now unique, and so I can use it with this function to produce whatever output I'm going to get. And so this lets us work with unrestricted things in the same way that we would work with unique things, as long as we're willing to make a copy. And one thing you might notice looking at these rules is that they're kind of similar to the shape of these two rules, which are the rules that define a monad in Haskell. So it seems like there's something algebraic, something mathematical going on here. And indeed what we have is that the share rule and the clone rule correspond very closely to return and binding monad, except that we have this additional modality present in the rules. So we have this additional star modality here and here in these rules. So what we actually have here, what this structure is that the bang modality is acting as a relative monad over the star. So rather than just a monad, we have a relative monad because of this extra modality here. There are some extra requirements for something to actually be a relative monad, but these things do hold this modality. So just a kind of interesting fact about the shape of what we have here. So now just to sort of clarify what's happening, here's a bit more of a practical example like we had with the file handle earlier. This one makes use of mutable arrays. So here, on this first line here, we're creating a reference to a new array that we're constructing in memory, and that array is going to have size 3. So here's an illustration of what's happening there. We have an array of size 3 with 3 cells, all initialized to 0, 0. On the second line, we write to that array. So we're writing to position 1, and we're writing the value 4.2. And when we do that, because we know we have the unique reference to this array, it's safe to do this in a mutable way, like in place. And so we can destructively change that cell in memory, that cell number 1, to be 4.2. So on this last line, when I read from the array at position 1, I get 4.2 back. This is in contrast to standard sort of functional arrays, which we also have in Granule. You can see this little I after the name of the primitives. That just means this is the immutable version of the primitive. So here, when we write to the array on the second line, what actually happens is that this reference A prime now points to a completely new array in memory. We are basically creating a new array that just has this one value changed. And this is fine in the sense that it's safe, just like it was safe on the previous slide. But it's not fine in the sense that this is now a little bit more inefficient, because eventually the garbage collector is going to have to clean up all of these extra copies, and that has performance costs. So one nice thing about being able to combine sort of uniqueness and unrestrictedness and linearity is that we can mix and match these two things depending on what's most convenient or most useful at the moment. So here what we can do is we can create a reference to a unique array. We can write to that array, so this happens destructively like 2 slides ago. But then if we need to use that array in an unrestricted way going forwards, we can share that, and then we end up with a functional array that we can use in a functional way. So we are able to mix and match and use these things in a safe way as long as we follow the rules. Okay, so that's a great start, and that covers what we did in our ESOP paper a couple of years ago. But now we need to move on to this idea of ownership and borrowing as in Rust. And this is all material from our OOPSLA paper, which we are presenting on Wednesday morning. I'll not have time to go into much detail now, so this is basically an advertisement for that talk. So you should come along on Wednesday morning if you want to know more. But the model of ownership that we like to use to think about how we're going to embed it in Granule with these ideas is that ownership is closely related to capabilities, as we've heard a lot about today. So if I have full ownership of a value, that comes along with the capability to do what I like with it. I can read from the value, I can write to the value, I can throw the value away, I can do what I want. What borrowing lets us do is it lets us split these capabilities into pieces. So what we can say is, for example, if I do this, which is what's called an immutable borrowing in Rust, what I'm doing is I'm giving part of the capabilities of that value away to someone else, the borrower. So what I'm saying is the borrower is now allowed to read from that value, but now we're both only left with the capability to read. Neither of us can write because that would lead to data races, all kinds of memory safety issues. On the other hand, I can also do a mutable borrow, so I can give the full capability, the full access to that value to someone else. They're now allowed to read from the value, write to the value, but that means that I'm not allowed to access the value at all, because since they might be writing, I'm now no longer able to read or write. Obviously quite a simplification. We don't cover all the details of ownership in Rust. This is just sort of representing some of the more simple ideas, but not too dissimilar from the conceptual model that Will was talking about earlier on in his keynote. So just a few examples of how that looks in Rust programs, just so that we can think about how we're going to represent those in Granule. Here we're just using a simple example where we have a struct that represents colour with 3 components for the red, green, and blue values of that colour. And then we define one example of a colour, which happens to be the nice shade of Granule blue, not advertising or anything. So here we have an example with 2 immutable borrowers. So both of these references are allowed to coexist because both of them are only allowed to read from the value. So this is okay. We're not allowed to have 2 mutable references because then they would both be able to write to the same value, which isn't safe. We can't even have a mutable reference and an immutable reference, because we can't have someone writing while someone else is able to read. That can also lead to problems. One interesting thing we can do, though, is we can create a mutable reference, and then we can create a mutable reference to that reference, which is sometimes called reborrowing. And this is completely safe, because at each step in that chain, the full capability is being passed along to the next borrower. So by the end of this small program, Y has the full capability to read and write, but X doesn't have any of the capabilities, and Granule doesn't have any of the capabilities either. So this is safe, it's fine. So now, how are we going to represent this in a graded type system like Granules? Well, it turns out that just like we can generalize linear types to allow for more precise quantitative restrictions, so for example, I can say I have something that needs to be used 3 times, I use it once, and then I have 2 uses remaining, which links really closely to ideas from bounded linear logic, as we mentioned. We can instead generalize unique types and get this kind of borrowing behavior, this kind of being able to split up the guarantees. So what we do is, the way that we do this is we start with a unique type. When we mutably borrow, we give that a grade which represents how much of the capability that value now has. So here, this has 1, which represents the full capability, so we're allowed to read and write. Now what we allow is we allow for this to be split up, and we represent that with fractions. So when we split that up into 2 references, we now say that each of these has a grade of 1/2. What that means is we no longer have the full capability, so we're only allowed to read at each of these references. And that holds until we recombine them and get the full capability back. And to get this kind of reborrowing behavior we saw on the previous slide, we can also split these up further. So we can have arbitrarily small fractions and still be able to read through all of these references. As long as, in order to be able to write again, we have to combine them all back up again to get back to the full one, the full fraction. So this is the sort of general way this kind of system works. And this is obviously based on ideas from Boylan's fractional permissions, which I'm sure many of you have heard about. But here they're sort of directly in the type, and they're being used as a grade on this new modality. Okay, so that's most of what I wanted to say. Again, that's just sort of a preview of all the technical details, which I'll go into a bit more in my talk on Wednesday. Just a quick sort of recap, I guess, of some other things that I've worked on that are kind of related, which you might be interested in. First of all, we've also looked at how communication works in this kind of setting. So it turns out that just as you can use session types to embed ideas about linear communication, we can also represent some forms of nonlinear communication by introducing grades. So just as we can generalize linear types to graded types, we can generalize session types to graded session types and get some kind of nonlinear communication patterns. So if you're interested in that, that's something you can talk to me about. Also, some ideas about security. So we had a talk about information flow earlier on, and that kind of links to some of this. So one other thing that graded types can do, rather than just talk about how many times something is used, is they can talk about information flow. So we can say that we're not allowed to take something with the private grade and turn that into something with the public grade, because that's illegal according to the rules of information flow. But something that's interesting is, if we think about how to sort of dualize this in the same way that we dualize linearity to uniqueness, then we get this idea of integrity, which is where, just as this is telling us, if we have something that's private, that's never going to be leaked in the future. Integrity tells us that if I have something that is, we call it trusted, then that means it's never been at the public privacy level in the past. So this is dual to confidentiality in the same way that uniqueness is dual to linearity. So those are just a couple of bonus topics that I'm happy to chat about. Otherwise, I must have finished. So here's just a quick summary of what we talked about. I guess the key point, really, the key takeaway is linearity is a restriction on the future. Uniqueness is a guarantee about what's happened in the past. So in some ways, they're similar. This is the key way in which they're different. Quantitative types, like you may see in Idris or in the linear Haskell extension or in Granule, are a generalization of linear types. They let us be more precise about exactly how something is going to be used rather than just linear or nonlinear. Meanwhile, borrowing allows us to generalize uniqueness, which gives us more flexibility. So we're allowed to create more than one reference as long as we do it in a safe way where we get back to the unique reference at the end. And graded types are a nice, powerful framework that let us embed all of these above things to some extent, and also various other things that I've just quickly mentioned. Here's where you can find out more about Granule. Please feel free to have a look. Here's where you can find out more about me, get in touch with me, and so on. Otherwise, thank you.
So maybe this is coming in the more details part later, but I was curious about fractional permissions because, I mean, you showed how they work in a classical way, but of course, in many programming situations, maybe you don't know the exact fraction. Is that something you're able to, is that something you can parameterize over? Is that something you can compute with? Just curious about, how far you go in that space.
I have a couple of answers to this. The first answer is that just like you can be polymorphic on the grades, like I showed earlier, you can be polymorphic on the fraction. So I can say if I have some fraction f, and I split that up, I end up with two references that have fraction f over 2. That's totally fine to do. The second answer, which is maybe answering a slightly different question, but I kind of want to talk about it, so I can talk about it anyway, is that you might think, well, we have all these different examples of grades on the previous slide. I've gone too far back. But we only have this sort of one example of something that we can grade this new modality by. Are there any other kinds of things that we can grade this modality by that talk about sort of different properties? We have thought about this. One example we've thought about is what we call counting permissions. So we can say, for example, we have the one reference that keeps a precise count of how many other references exist. All the other references are just sort of read-only permissions. And then once all those are gathered back, we end up back at 0 of their existing references. Then the benefit of that over this is we are able to know exactly how many other references exist. The downside is we have this kind of asymmetry, so you end up with one privileged reference that knows this number. All the other references are just sort of read-only and don't have that ability. So that's probably more useful in some situations, less useful in other situations. I'm sure other things that you could put on this modality exist as well. That's something else to think about in the future. This is just one example of how this sort of works.
Thanks.
One of the strange properties that, for example, linear Haskell has, and which distinguishes it from linear logic, is that they have this distributivity law. So you identify, of course, A tensor B with, of course, A and of course B. And I was always wondering, do graded model types have an answer and let you express the thing that you can have infinitely many A's and B's, but exactly as many A's as B's?
This is a fantastic question because I have a paper about it, so it's always fun to have that. First of all, you should look at that paper. It's called Linear Exponentials as Graded Model Types. It's from a couple of years ago now. The answer is that in most graded type systems, of which linear Haskell is an example, and Granule is also an example, it's usually been the case that we have this kind of distributive property. So you can say, I have bang A tensor B, and we can distribute the bang A to the tensor and have bang A tensor bang B, which is not present in linear logic. So what the paper is about is, can we actually embed linear logic in a graded type system given that there's this weird sort of difference? And in that paper we kind of come up with a bespoke solution, which I won't go into too many details about how you can add some extra stuff to the type system to allow you to do that. But the answer really is that for some reason people who implement graded type systems have found it more useful to have the distributivity and not exactly match up with linear logic. If you want linear logic, you can change some things to make that happen, but it is true that a lot of graded types systems differ in that way. Yeah.
Any more questions? I have a question. So you talk about unique ownership, right? So one way to think about unique ownership is that it's essentially incidental ownership. I mean, I happen to know that I am the only one who owns a reference to something, so therefore I own it de facto. But like there are a lot of ownership holders that are not using uniqueness as ownership, and we had always saying in the previous talk that this was a showstopper for what they were giving its with. So what's your next step to overcoming that?
It's a great question. I mean, well, first of all, this kind of borrowing model is a way to get away from that to some extent. Like, you start from this
right, but in this broken Rust model where borrowing also has immutability tagged on as an unwelcome.
Yeah. So, but yes, it's an interesting question as to maybe, like you were saying earlier, there are ownership models that don't even necessarily talk about how many references exist. They instead talk about what exactly am I allowed to do with this value and what permissions do I get from the owner. And it's an interesting question as to whether these grades could be used to kind of embed that, because as we saw with the other kinds of grades for linear types, we're not only able to talk about how many times something is used, we're also able to talk about things like security levels, that kind of thing. Can we put some other information on this modality rather than just a fraction or a number that tells us something about, I have this kind of information, I'm giving this kind of information to the borrower? That would be cool. Maybe there's some kind of general algebraic structure like we have with the semi-ring over here can be used to do that. But that's definitely future work. I don't know the answer to that, but it would be very interesting to think about.
Anyone else? More questions?
Yeah, thanks again for another lovely talk that explains stuff I've been trying to get my head around. I think we're asking everybody to dump their slides on the web page, if that's okay. You did say you were working from a linear basis. I guess I'm asking how important that actually is. I mean, is it just a question of what's the interpretation of a single arrow type? And then you've got the rest of the mechanism built in? Or is there something else going on there?
So this is an interesting question because it's something we've thought about. Sorry, there's a lot of...
I'm deaf and there's a lot of noise next door.
Yes. So this is something that we've thought about a lot in the context of between different graded type systems, there are a few different ways that this has been done in the past. So some graded type systems have a linear basis where things are linear by default and then you have a modality added on which represents graded things. Some type systems have what's called a graded base, which is where just everything has a grade. So function arrows have a grade on them and then you go from there. And that grade can be 1, in which case it's linear. Otherwise, you have the grade that tells you how that was used. What exactly the relationship is between these two systems is something that we've been thinking about and writing about. It's not quite out there yet, but I think the sort of key answer is it is possible to sort of translate between these two systems. And so maybe the answer to your question is it doesn't really matter if it's more sort of detail about what you want to privilege in your language. It's like, do you want things to be linear by default and that's the easiest thing to write and the graded things are added on? Do you want things to be all graded, which the program always has to think about the grades? It depends.
And based on earlier discussions with people, I was going to ask you what the difference between effects and co-effects was, but I'm afraid we're out of time for you to answer.